Live.
Hi everyone, welcome again to the Shannon channel. Today I'm very happy to have Denali Molitor from UCLA, and she's going to give us a nice talk on randomized Kaczmarz with averaging.
Thank you for the introduction and for the invitation to speak. So I'll go ahead and start sharing slides. Okay, so today I'll be talking about the randomized Kaczmarz method and a parallel version that uses an averaging of independent updates. And this is work with Jacob Moorman and Thomas Tu, who are also PhD students in mathematics at UCLA, and along with Professor Deanna Needell, who is my PhD advisor. Okay, so the goal with the Kaczmarz method is to solve large linear systems of the form AX equals B. And here we're assuming that the matrix A is highly overdetermined. So we have many more rows in our matrix than we do columns. We're also assuming that our system is large enough such that it can be inefficient or infeasible to solve for the solution vector X directly. For example, by doing something like using the QR decomposition to compute the pseudo-inverse. And in this situation, it can be more efficient to use iterative methods to solve for X or approximate X rather than computing the solution directly. Okay, so this is sort of the goal of, or the problem setting. And the Kaczmarz method is one iterative method for producing or solving this sort of problem. So today I'll talk about the Kaczmarz method and the randomized version of it or extension to it. I'll talk about how this method relates to stochastic gradient descent, which is a popular method for stochastic optimization in settings such as machine learning. I'll talk about a basic convergence analysis of random Kaczmarz, and this analysis is similar to the analysis that we use in the parallel averaged version as well. And then I'll talk about the parallel method that we've been working with, show some experimental performance for that parallel version, and talk a bit about hyperparameter choices involved with the method. Okay, so the Kaczmarz method is an iterative method for solving linear systems of equations. And at each iteration, we take the current iterate and project onto the solution space with respect to a single row of our matrix. So here we had the linear system AX equals B, and A sub I will just denote the ith row of the matrix A. And in the original Kaczmarz method, which was proposed in 1937, one would just cycle through the rows of the matrix and do these projections cyclically through the matrix. So we'd start by projecting onto the solution space with the first row, and then the solution space with the second row, etc. And the Kaczmarz method has been sort of rediscovered several times in the last few decades, or in the last many decades. So in 1970, it was rediscovered and coined as the algebraic reconstruction technique by Gordon, Bender, and Herman. And specifically in that setting, it was used in computed tomography and has been implemented in medical scanners since the 1970s. So in computed tomography, we have an X-ray that sends rays through, for example, a person's body and calculating or sensing the densities of material. And it does this from various angles. And based on those measurements, we'd like to reconstruct an image or a 2D or 3D representation of the densities of, say, organs or bones within a person's bodies. So here's sort of a graphical example of how computed tomography works. And this image on the right-hand side is, for example, what we're interested in reconstructing in that setting. Okay, so we can also sort of geometrically see what is happening when we apply the Kaczmarz method. So in this example, we assume we have some matrix A, and each of these lines represent the solution space with respect to a single row of that matrix A. So along this line, all of these points X are such that their inner product with the ith row of A is equal to B sub I. And in the Kaczmarz method, we'll first look at the first row, which I think is this row here. And we project our current iterate X naught onto the solution space with respect to that row. And doing this, we get closer to the true solution here in the center, which occurs at the intersection of all of these solution spaces. So now at the next iteration, we look at the second row and the solution space with respect to that row, project there, and get closer. We look at the third row and project and get even closer to the true solution. However, with this cyclic ordering of the rows, we could potentially end up with a very unlucky ordering of the rows. So for example, if we have these solution spaces, if we sort of had the rows in order of being closest to our current iterate, when we project, we don't make that much progress towards the true solution. So in this case, if then we're projecting onto the next row to the left, we're only very slowly converging to the true solution in the center. Unfortunately, if we just cycle through the rows cyclically, we could end up with an ordering that leads to a very slow convergence rate. And this is the motivation for using a randomized version of the Kaczmarz method. So that in randomized Kaczmarz, instead of cycling through these rows, we will pick indices from some distribution or with some randomness and project onto that row so that we don't have to worry about our matrix having a particularly unlucky ordering. And I forgot to mention, but at each iteration, the update is just given in this form. And so it's a very simple update that we're performing at each iteration. So when we add this randomization, we don't have to worry about being stuck with a particularly bad ordering, but we also don't necessarily get to take advantage of particularly good orderings either. So it could happen that you know some additional information about the rows of your matrix that could give you a particularly good ordering in which to perform these projections. And also there are certain heuristic choices that are commonly made in practice. So for example, if we're sampling the indices from some fixed distribution, there's the possibility that we could sample the same row twice in a row. And in that case, we would make no progress with that additional update since we're simply projecting onto the space that we already lie in or that our current iterate already lies in. So oftentimes this randomized Kaczmarz is combined with some heuristic choices such as sampling without replacement when we sample the indices, or for example, just using a different random permutation of our rows at each time going through all of the rows of our system. Okay, so the randomized Kaczmarz method can also be related to the stochastic gradient descent method that's commonly used to optimize loss functions in machine learning. So oftentimes loss functions take the form of being a sum of component functions, where the number of component functions here can be very, very large. So for example, in a machine learning setting, this may represent the sum of losses with respect to individual training data points. And one popular and simple way of optimizing such a function is using gradient descent. And as to recall what gradient descent is, we basically, from our current iterate, we calculate the gradient of the function and then take a step in the direction of the negative gradient. So here this eta parameter is indicating a step size. Stochastic gradient descent, which is popular in practice, instead of taking the full gradient at each step, looks at the gradient of just one component loss function or a batch of component loss functions. And this way, this gradient calculation is much faster than calculating the full gradient. And so we hopefully are able to make progress towards a minimizer much more quickly. And here in this setting, we're using these the gradients of the component losses as an estimate for the full gradient. And in a 2015 paper, Needell, Srebro, and Ward showed that the randomized Kaczmarz can be viewed as reweighted SGD with importance sampling applied to the least squares loss. So sort of going into what I mean by reweighted and using importance sampling, here with the importance sampling, we're going to pick component functions with a non-uniform probability. So a popular strategy for picking rows in the randomized Kaczmarz method is to pick the rows with a probability proportional to their squared row norms. And so in this case, this would be a non-uniform probability. And when we do this, we need to account for those non-uniform probabilities in the SGD update so that we still have these steps, so these gradient calculations being an estimate for the full gradient. So now we can have the probabilities be absorbed into the step sizes of this reweighted SGD, or the step sizes are weighted by the probabilities. So we can see algebraically how we end up with randomized Kaczmarz from this SGD process. So if we look at the gradients of the component functions when we're considering the least squares loss, the gradients take this form, where again here A sub I is just the ith row of the matrix A. And if we pick the rows with probability P sub I, then when we do this reweighting process, so this is just the 1 over P sub I, and if we plug in this component gradient, we get exactly the Kaczmarz update. Although here there's a coefficient outside weighting the step size that we're taking. And here just also of note, this A sub I is a row vector, X is a column vector, so this quantity here is a scalar. And so on some of the slides, depending on what we're looking at, it'll be convenient to write this AI transpose on either side of this scalar value. Okay, so now I'll give an overview of the convergence of randomized Kaczmarz. And a lot of the extensions to randomized Kaczmarz or similar methods have very similar convergence arguments. Okay, so here I've written again just the randomized Kaczmarz update. And this analysis is coming largely from a paper by Strummer and Shannon in 2009, as they were the first to show that the expected error squared norm converges exponentially. So here, starting with the initial update, we'll just subtract the true solution from both sides. So X star here, we're assuming is an exact solution to our linear system. So we're assuming that although our linear system is overdetermined, there exists a solution X star that solves the system exactly. And later I'll talk about what happens when this assumption doesn't hold. Okay, so reorganizing on the right-hand side. So in practice, we won't actually know the value of this X star. And so our update can't include the knowledge of the true solution. And so our update instead depends on this difference, the AIK XK minus BIK. But if we're assuming that X star is the true solution, we know the inner product between X star and A sub IK is just equal to B sub IK. So now we have pulled out an XK minus X star sort of in these first two terms, and this is representative of the error at the kth iteration. So grouping these, we then have the following form, and we'll now take the norm of both sides of this equation. So we're interested in getting a bound on the expected value of this error norm that depends on the error at the previous iteration. And using orthogonality, or equivalently the Pythagorean theorem, we have that this matrix here is just the projection onto the vector AIK, And so we have orthogonality between these two vectors, and we can decompose the norms in this way using the Pythagorean theorem. Okay, so now when we take the expectations, we're going to condition on our current iterate. And we can pull out this first term since we're conditioning on xk, and then incorporate the probabilities here that we're sampling, or with which we're sampling each index. And here we're using these probabilities where they're proportional to the squared row norms of each row. Okay, and looking further into this squared norm that we have on the right, we can simplify that expression. So again, this AI times xk minus x star, this is just a scalar value, so we can pull that outside of the norm. And then we're left with the norm squared of the ith row, which then cancels with with the norm squared in the denominator, and we can simplify to the expression on the right. Substituting this back into the equation above, and then also canceling the remaining norm squared of the row that we have here with the second row score, or norm squared here, we get this expression. So this is, the algebra here is what motivated this non-uniform sampling of the rows, or this specific probability distribution with which we're sampling the rows. Because now when we take this sum over all of the indices I, we have that we can express that sum as just being the squared norm of A times the vector xk minus x star. So now if we want to write something, or we can bound this term from below so that we get an upper bound on this expected error by using just the minimal singular value of the matrix A. Are there any questions so far on the convergence analysis?
I think no questions so far.
Okay, great.
Thank you.
Mm-hmm. All right, so now just pulling out the xk minus x star norms, we arrive at the convergence rate that Stromer and Shannon proved in 2009, which is that the expected error norm squared is less than or equal to this constant times the expected error norm of the previous iterate. And since this term here doesn't depend on our current location or current iterate, we can unroll this recurrence and get a convergence, or a bound on the expected error that's based on the initial error. So as I mentioned previously, here we're assuming that our linear system AX equals B is overdetermined. And so it's not realistic to always assume that there exists a solution X star that satisfies this equation exactly. And so what happens in the case where we have noise in the system? And in this setting, we're typically interested in finding the least squares solution to the problem. So this is the problem that we'll consider next. And for simplicity, we'll assume that A is full rank, but there are papers that sort of discuss how to get around this, this technicality. So geometrically, what happens when we have noise in the system is that the solution spaces with respect to each row no longer all intersect. So in particular, there will be at least one of these solution spaces that doesn't intersect the least squares solution. So if we again go through the Kaczmarz method or the randomized Kaczmarz method, selecting a solution space and projecting on to that specific solution space, picking another, projecting on, we initially have convergence that looks similar to the original Kaczmarz method applied to a system that didn't have noise in the system. However, once we approach the least square solution, we start to sort of bounce around quite a bit and we won't actually converge to the least squares solution. We'll only converge to within some convergence horizon of the least squares solution. And this is happening because of the fact that we have at least one of these solution spaces that doesn't intersect the least squares solution. So in the noisy setting, Nidal and then Zuzius-Freris proved bounds on Kaczmarz in this setting. So the first part of this bound is just the same convergence rate that we had in the consistent case, so the case where we don't have noise. And then due to the noise at each iteration, we also have an additional term where this R star is just the least squares residual. So this is the difference between AX star minus B. And again, you can unroll this recurrence and keep track of these terms that come out of it and get a convergence bound that depends on your initial error and then also the least squares residual. Okay, so now I'll introduce the RK with averaging method that we've been investigating recently. So going back to the initial RK update, one drawback to the randomized Kaczmarz method is that it operates sequentially. So each new iterate xk plus 1 depends on the previous iterate xk. And in particular, this is undesirable because it limits the amount in which you can sort of take advantage of parallel processing. So you can do some of the matrix operations in parallel, but each of these iterations is generally pretty quick and simple, and so we'd like more ways to incorporate parallel computations. And one extension to the randomized Kaczmarz method that we saw briefly earlier in the context of relating to SGD is the relaxed randomized Kaczmarz method. So here we incorporate a parameter that we can think of as being a step size towards the projection. And so, for example, early on in applying this method, you may want to choose this parameter to be larger to sort of accelerate convergence. And then as you approach the least squares solution, especially if you suspect that there's noise in the system, you might decrease this parameter to sort of dampen the effect of the noise. So we have been considering a simple parallel extension in which we use a weighted average of independent updates. So here we have the same Kaczmarz update where we take a weighted average over some set of independent updates. So tau sub k is indicating the set of indices that are considered at each update. And these WIs are a weight that corresponds to each of the rows in the system. So now we could, for example, compute each of these calculations independently in parallel threads, and then combine this information to hopefully have an update that makes more progress than a single update would. So the size of the set tau sub k will just relate to the number of threads, for example, that we're assuming we have available. So I'll introduce some notation that will allow to explain this method a little more concisely. So we have a normalization matrix D, which is a diagonal matrix that contains the norms of the rows of the matrix A. So that when we have the matrix D inverse A, that will be a matrix whose rows have unit norm. We'll also use a probability matrix P, which is again diagonal and has just the probabilities of selecting each row at each selection step. So it's possible that in our set tau sub k that we're using at a single iteration, that we could select the same row multiple times. And this choice just allows for an easier analysis of the method, although in practice wouldn't make that much sense to actually do. And we'll also have a weight matrix W, which is a diagonal matrix with with positive weights. And each of these weights corresponds to a row in our matrix A. Okay, so here I've shown the update for this parallel random Kaczmarz with averaging again. And it's going to be useful to sort of isolate this sampling process that we're performing. So here we've just moved this AI transpose to the other side of the scalar value and then pulled the A's out from the sampling process. So this bold I sub I here is the ith row of the identity matrix. With this formula, we can then consider what happens as we send the number of threads or the number of indices in our set tau sub k to infinity. And as we do this, this sampling matrix approaches the expected value given here. And in particular, we now have a deterministic update. And we can calculate this expectation as being just the matrix product of PWD inverse squared. And since we want that the method will converge to the least square solution, it's reasonable to require that the least square solution be a fixed point of this update. So here I've replaced that expected value with what we calculated it to be, which is just the matrix product PWD inverse squared. And we can see that if x star is a fixed point of this equation, then it must solve this equation here, which in particular corresponds to the normal equations of the weighted least squares problem, to this weighted least squares problem where this norm with respect to this matrix is just given by this formula here. So we would have b minus ax, comma, PWD inverse squared, and then b minus ax again. And when we have a consistent system, the minimizer of this least squares problem will just give us a value here that's 0. But for inconsistent systems, if we want the minimizer to correspond to the typical 2-norm minimizer, then we need that the matrix product PWD inverse squared be proportional to the identity matrix so that we can pull that value out of this norm. If we don't satisfy this condition that the matrix product be proportional to the identity matrix, then what we're really solving with this method is this weighted least squares problem as opposed to the least squares problem with the 2-norm. So we'll typically assume that we have this restriction on this matrix product, and we'll think of alpha as sort of a relaxation parameter or a magnitude of these weights and the update.
I have a quick question. So you probably mentioned it. How are you sampling the columns together or the rows?
We're sampling the rows with probabilities that are given in this P matrix. So I think I have it, yeah.
And you will design P.
Yes, we choose, yeah, so that's a good point. So we choose the matrix P and the matrix W. Those are both like parameters that you feed into the model. And then the matrix D is given by, that just contains it's a diagonal matrix with the rows of A, or the norms of the rows of A. And so we don't have control over D, but we do control the matrices P and W. So
I forgot.
What was that? Sorry.
Yeah, what is W? I forgot what is W.
So W is a diagonal matrix as well. And the diagonal entries of W are coming from the weights that we're using in this weighted average. So W will be a diagonal matrix with positive entries, and the weights are going to be the weights that we use in the average.
Okay. Yeah, thank you.
Yeah, so in that, like relating to that question, when we require that we have this condition on our matrices, we're really finding we have a coupling between our choice of P and our choice of W.
So if you take the special case where W is like all ones and you're sampling uniformly, does this give an interesting thing? Or what would that give?
Yes, so in that case, this condition is not satisfied because the matrix D will typically not have all ones. So if P is constant or is just has constant values and W is uniform, then D would also have to be uniform in order to correspond to like satisfying this condition. And I'll show some experimental results of what happens in that case.
Okay. So I don't know if I'm, maybe you're gonna talk about this, but if you, I mean, how does this relate to, for example, to batch SGD, where you just, is it related to batch SGD where you just sample the batches uniformly?
It is related to batch SGD in sort of a similar way to how Kaczmarz is related to just SGD. And so in the batch SGD case, we would also sort of normalize by these probabilities in the weights, or it would suggest normalizing by the probabilities in these weights when you're accumulating the component gradients.
Okay, thank you.
Yeah. Mm-hmm. Okay, so with this random Kaczmarz with averaging, we're able to prove a convergence result on the expected error. So here this EK vector is just our current error, so xk minus x star. So we can get a bound on the expected error in terms of the error at the previous step. And the bound that's shown on this slide is not particularly interpretable, largely because we have this RK, the norm of RK squared with respect to the weight matrix W here. And this RK vector is hiding or depends on this EK vector here, in addition to depending on the noise of the system. So this bound isn't particularly interpretable, unfortunately. But we can, if we assume that W, or that the weights are uniform, so here W is proportional to the identity, then we can derive a more interpretable bound. So here we'll assume that W is just equal to alpha, which is a scalar, times the identity matrix. And in this case, we can decompose this norm with respect to W and pull out this alpha. So here we add and subtract x star to decompose b minus axk into r star plus aek. And since the multiplication in this norm by W results in just the multiplication by a scalar alpha, we can pull that out of the norm as well. Although I think that alpha there should be squared. That alpha, yeah, this alpha should be squared, not just a single alpha. And since we know that the residual, the least squares residual r star is orthogonal to the column space of A, we have that when we expand this norm here, that the cross terms cancel. And so we can isolate the norm of the least squares residual and the dependence on the current error AEK. And doing this allows us to write down a more interpretable convergence rate in the case where we're using these uniform weights. And that convergence rate takes this form. So now, since we're using uniform weights, we are sort of forced to pick probabilities that are proportional to the row norms. So the probabilities that Stromer and Shannon used in their convergence analysis of randomized Kaczmarz. And in this case, there are several things that we can notice about this convergence rate. So again, alpha is giving sort of this scaling, and it can be thought of as a relaxation parameter or a step size. And we have that this matrix here is just quadratic in alpha. And so one can find the alpha that optimizes this convergence bound by, in terms of the maximal and minimal singular values of the matrix A. Additionally, we can see from this term that the convergence horizon will be quadratic in alpha, and so having a larger alpha will amplify the effect of noise in the system. Also, here we can notice the effect of the number of threads on the convergence rate. So in this matrix, we have that increasing the number of threads will improve the convergence rate up to some threshold. So here we're sort of limited by this matrix here. And then we also have that increasing the number of threads will improve the effective noise or decrease the effective noise on our approximation. Okay, and in the setting of uniform weights and also assuming a consistent system, this method was analyzed previously by Richter and Kaczmarz under a more general framework known as sketch and project methods. So in our analysis, we look at the case where we have non-uniform weights and we also have inconsistent systems. And as sort of an aside, sketch and project methods are a class of randomized iterative solvers for linear systems, of which randomized Kaczmarz is like a special example. And in sketch and project methods, you use sketching matrices S to basically reduce the size of your system. So at each iteration, we project onto the solution space of a sketched version of our system, where solving for the solution space here is much easier than considering the full system. And in particular, if we choose the sketching matrices to just be the ith coordinate vector, we'll exactly recover the randomized Kaczmarz method here. But you can also recover other methods such as coordinate descent using the sketch and project framework, as well as like block randomized Kaczmarz methods where you consider multiple rows at a time. Okay, so now I'll talk about some experiments that demonstrate the convergence in practice of this parallel randomized Kaczmarz with averaging. So in the first experiment, we look at the effect of the number of threads on the convergence. So here, this is multiple trials of randomized Kaczmarz, of this randomized Kaczmarz with averaging applied to a 100 by 10 Gaussian system, or random Gaussian system. So the entries are just random Gaussian variables. And here we're using uniform weights that are equal to 1, and then probabilities proportional to the squared row norms. So in particular, we are satisfying this assumption that the matrix product PWD inverse squared is proportional to the identity. And we can see that as we increase the number of threads in tau sub k, we see an improved convergence rate up to some threshold, and we also see an improvement in the convergence horizon. So the convergence horizon is decreasing as we increase the number of threads. So in the figure on the left, this is a similar figure, except here we've chosen the weights to all be 1 and to use uniform probabilities. So in this case, we don't satisfy this matrix condition that PWD inverse squared be proportional to the identity. So this sort of relates to your earlier question. And again, here we see that increasing the number of threads in tau sub k improves the convergence rate, but we don't see this continual improvement in the convergence horizon as we increase the number of threads. And in particular, this is happening because we're approaching the solution to this weighted least squares problem as opposed to converging to the solution of the standard least squares problem with respect to the 2 norm. And in particular, or in this case in particular, since our system is just Gaussian, the difference between the weighted and the 2 norm version we expect to not be too large, but in other cases it could be. Okay, in terms of the effect of the relaxation parameter alpha, so that we have that as we increase alpha, we see an improved convergence rate up to a point. So if we make alpha too large, we'll see degradation in the convergence rate eventually. But we can also see in this plot that as we increase alpha, we have an amplified effect on the noise, which we also saw occurring in our in the convergence rate that we derived. So this is indeed happening in practice as well. And one thing that we haven't looked into in detail, but that would make sense to look at in terms of this plot, is using an alpha value that depends on the iteration. So initially you might want to use a larger alpha value to have fast convergence, but then decrease alpha so that this effect of the noise is not amplified. Okay, and in this plot, we are looking at like values of investigating which values of alpha are optimal. So on the y-axis, we've plotted the number of iterations required for our solution to reach to converge. So here we're considering consistent systems, and I think convergence was considered to be error within 10 to the negative 10. And on the left, we're using uniform weights and probabilities proportional to the squared row norms. In the right plot, we use weights that are proportional to the squared row norms and uniform probabilities. So in both of these cases, we are satisfying this matrix condition, but in slightly different ways. And although one can calculate the optimal alpha for the convergence rate, it doesn't necessarily correspond to the optimal alpha in practice. And this is just because the optimal alpha will depend on the current iterate as well as the spectrum of your matrix A. So while we can optimize the alpha for the convergence bound, it's more difficult to choose the optimal alpha in this way for the true optimal in practice. Okay, so in summary, I've talked about the randomized Kaczmarz method and sort of some of the history there and basic convergence analysis. I've also presented this parallel version of randomized Kaczmarz with averaging and shown some results in terms of how we can analyze the convergence rates and get guarantees in that case. And in particular, we find a natural coupling between the probabilities that you use and the weights that you use in this averaging. And we can prove the expected convergence rate per iteration in a general case and a more interpretable version for the simpler case in which we use uniform weights. And then we can also prove and demonstrate improved convergence with increasing the number of threads available. Right. Thank you all for listening. Are there any questions?
Thanks a lot, Denali. So I don't know. I'll see if anyone has a question, they can just ask the question. Let's wait and see if anyone has a question. So maybe I can start with the question. So and you already maybe answered part of it. So how would you relate this more to batch SGD? Because for me, what I thought, and again, so I maybe my information may be wrong. So that batch SGD will converge to the optimal, to the true optimal. Is that but then what I saw in your experiments is that it depends. If you don't use the sampling probabilities the right way, you're not going to converge to the true thing.
Right. So I think the complication that comes here. So I'll just go back to the slides that I had on SGD. So one of the reasons that SGD becomes, or one of the subtleties of relating SGD to the Kaczmarz method is that in the Kaczmarz update, we are performing a projection onto the solution space with respect to like a row. And so you're not using like a constant step size or a decaying step size in the same way that you typically do in SGD or like batch SGD. The projection sort of gives you scaling. And so in that way,
but you have in your there is eta is for SGD here.
Yeah, the eta here is relating to the SGD update.
Okay.
Yeah, so you get this sort of this rescaling with the probabilities there. So yeah, so there's sort of an interplay between the projection step and the probabilities and the getting the SGD formula to match up with the Kaczmarz update. And something like you have sort of a similar process happen with the parallelized randomized Kaczmarz, where you can relate it to mini batch SGD, but then also have to account for these probabilities, and those will sort of pair with the weights that you use. But you can relate the two still.
Okay. So I don't know if there's no one else has questions. I think so. The talk will be posted on YouTube, and then people can also comment and watch offline. I want to thank you again a lot for this interesting talk and the nice intro and the quick literature survey also. Thank you.
Thank you.